So the G-share predictor can be also depicted this way in hardware. You have the PC, some bits of the PC and the global BHR are going to get XORed, and that is going to be the index into the pattern history table. And then the decision is going to come. If it's taken, then that is going to select the target address, the branch target address. Otherwise, we continue with PC plus 4. So as you can see, all of this hardware has been the same since the beginning, just that the component to the left of this has changed, and this is how the G-share predictor is implemented. So there is, we've discussed G-share, and we also discussed G-select. Now the difference was that here you have an XOR gate and here you do not have an XOR gate, you just concatenate it. So you can think of it this way. Whenever you have an XOR, they just change the name from G-select to G-share. So similarly, uh, if you have a global register, such as a branch history register, you just call it a global predictor. Whereas if you have a local BHT, this is called a local predictor. So this is also called as per address uh, predictor, because you have a branch history table for every address, and that's for the local address. So those kind of predictors which have the BHT are also called p-share predictors. So this is just a different terminology for the local predictors that we had seen before. So all the local predictors that we had seen before, if they were to use an XOR gate instead of concatenation of the PC and uh, the BHT entry, they would be called as p-share. So this is just a different variant. Okay, so the difference is just shown here. In case of a G-share, you have a single BHR, whereas in case of a p-share we have the uh, BHT, and in both of these cases we are going to concatenate with we are not going to concatenate, but we're going to use an XOR gate. That is why it's called a G-share or a p-share predictor. Now if you look at this particular paper by A and Pat, they show three different implementations of what we have seen so far. So this is the GAG predictor, which means you have a global branch history register and you have a global pattern history table. So that is, the first G is for the global branch history register. The A stands for adaptive, and the next G stands for global pattern history table. Now this could be with or without the PC. Then you have another type, which is PAG. P is per address branch history table. So basically for every address. So it says every address, but of course we are not going to have it for every different address. We are going to use some bits of the PC to index. So, but still it is not a global history register. It is a history table. So that is why it's called a per address branch history table. And then you have the global pattern history table. That's why it's called PAG. You could also have another type. You could have a per address branch history table, and you can index into separate pattern history tables. So this is going to be more complex and probably more accurate, but this is going to consume a lot of area. So I have just explained the same things here. You could also refer to this paper here. So GAG means a global BHR and a global PHT. So both the branch history and the pattern history for the branch are going to be dependent on the outcomes of other branches. That's why both are called global. So it is not dependent on just that local branch, but it is also dependent on other branches. So both of them are global here. In a PAP, both the BHT and the PHT are going to be local to the branch's own history. It doesn't depend on other branches, and therefore both of them are called per address. Whereas the other type, the PAG, the first one, the BHT, is going to be dependent on the branch's own history, whereas the pattern depends on the global entries. So this pattern history table is shared by all other branches, whereas this BHT is per address. So if you could refer to this paper, they have more explanation on which one is better. So which one is good? So the answer is it depends. So you could read the section 5 here. Uh, but overall, compared to the single level predictors like the 1 bit or the 2 bit that we had, these 2 level predictors, which have the history of the predictor, which have taken account of this history, they achieve a much better accuracy. So there are of course more predictors. So the predictability depends on the type of the branches. The global history may work for some, local history might work for some. There are also hybrid predictors which select between different types of predictors. I'll explain one such predictor in the next slide. There are also perceptron based predictors these days, which use machine learning for prediction. So it basically learns the relation between different branches, assigns weights to these correlations, and so on. So we look at one type of hybrid predictor. It's also called tournament predictor. So what this does is it chooses between two types of predictors. So we have seen this kind of an FSM before, where we were choosing between two states, taken and not taken, and we had basically divided this into strong and weak, and this again into strong and weak. So something very similar to that can be used to choose between two different types of predictors. So usually the choice is between say G share and P share predictors, that is global and local predictors. And this tournament predictor is also a very popular predictor. You can refer to these two video lectures if you want to understand more about this, more than what I'm explaining now. So just to explain this FSM, so let us say we start off in this particular state here, where we say use predictor 1. So this predictor 1 could be, for example, G share. So you will go ahead and take the predictions from the G share predictor. Now, after you calculate uh, the EX stage of the branch and you actually resolve the branch, you will find out if the prediction is correct or not. That is, you will find the actual outcome. And when you find the actual outcome, let us say we figured out that predictor 1 was correct and predictor 2 was incorrect. Then what you do is, so this is 1/1 means predictor 1 was correct and predictor 2 was correct. Both are correct. So then we continue in the same loop. That means we continue using the same predictor. If it is if it is let's say 0/1, for example, then it means the predictor 1 which we used was incorrect and predictor 2 was correct. So then what we do is we change our state. So this is still going to be using predictor 1, but we can think of this as use it with less confidence. So just like the way we did strongly taken and weakly taken, this first one can be thought of as use it with a higher confidence, and the second state is use it with a lesser confidence. So now again, let us say this predictor 1 goes wrong. So if this predictor 1 goes wrong again, this means that it is again going to give us this kind of an indication where predictor 1 is wrong and predictor 2 is right. Then what we do is we change the state and we use predictor 2. So this is like you have to go wrong twice with the same predictor before you switch the predictor itself. So similar to our FSM that we had earlier, the 2-bit counter FSM, we had to go wrong 2 times before you change the state from taken to not taken. Now you're changing the predictor itself. So of course you would have now guessed that if again this predictor 2 is, uh, let's say if the predictor 2 is going to be correct again, then you're going to go to the state. That means use it with a higher confidence. So this is how the tournament predictor works, and this is also a very popular predictor. So you have, this is of course definitely more hardware because you are implementing two different types of predictors, and you're also trying to choose between the two with extra logic here. So this is definitely more effort. So what are the typical predictors used these days, and what are the entries, number of entries in the BTB? So typically 4096 entries are used in the branch target buffer. G-share is a popular predictor, and hybrid predictor or the tournament is also usually used. AMD uses G-share with 8192 BTB entries and it's reported 95% accuracy. Pentium Pro uses a two-level global predictor. So this is similar to our G-share with a 4-bit history and multiple PHTs indexed by the PC. So if you have a multiple PHTs, you can now think whether this was a G-share predictor or another type of predictor, but still it is a two-level global predictor. Then you have the Intel P6 architecture, which uses a 4-bit history, global PHT. It uses 2-bit counters, 512 entries in the BTB, and the misprediction penalty is 15 cycles. So it means that this has probably a 20-stage pipeline, and the accuracy reported is about 90%. So that completes the topic on branch prediction. I've taken several contents from all of this and duly acknowledge it. If you want to read more about correlated branches, there are some references here which you could use.